Welcome to section 7.1. We're beginning a new chapter, chapter 7. And chapter 7 is called the normal probability distribution. So we're going to discover a new distribution. And the difference between this and chapter 6, in chapter 6 we are dealing with discrete random variables. In chapter 7 we're going to be looking at continuous random variables. All right, so section 7.1, we're going to be just looking at the properties of the normal distribution. So we remember that when we classify continuous random variables, we use intervals. And now that it's a probability distribution, each interval will have its own probability of occurring. Let's look at a very basic example. We have that a peer always arrives 0 to 15 minutes late to class. We could say it's equally likely that the peer arrives 3 to 4 minutes late or 13 to 14 minutes late. In other words, all intervals of the same length are equally likely. So the random variable x can be any value in the interval 0 to 15. The random variable x takes on any value between 0 and 15 minutes. And because each interval is equally likely, x follows a uniform distribution. All right, and again, if you wanted to clarify what x is the random variable, and it's the amount of minutes late. All right, so let's consider the following. We're going to be looking at probability density functions, or PDFs, and it's an equation used to compute probabilities of continuous random variables. And it has two properties. The total area under the graph of all possible values, the total area must be equal to 1. And then the height of the graph has to be positive. So it has to be greater than or equal to 0 for all possible values of the random variable. So this is like our probability distributions when the area, when we added up all the areas, it equaled 1. And all the probabilities have to be greater than 0. Okay, so let's graph the example above. So from what we just said, we know it has to be positive. The height has to be positive. X is going to be horizontal, so it'll be number of minutes late. And X can be from 0 to 15. All right, and this is a PDF. So the height is the PDF, the probability. And then we can sometimes call that the density of the function. Okay, so since each interval is equally likely, the probabilities are all the same, and so it's uniform, which means the graph looks like a rectangle. Okay, so there you go. So let's focus on that first part of a probability density function. The total area has to be equal to 1. And so let's see, the length, 0 to 15, is 15, and we have to essentially figure out the height of this rectangle. So base times height is the area, and we know that the area, the total area under the graph, has to be equal to 1. So we have to solve this. So how do we solve for h? Let's divide both sides by 15. And so that means this mark right here is 1 over 15. That's the height of a rectangle. Okay, so now we want to find the probability that the student is 5 to 10 minutes late. So let's maybe, it's like cutting it in thirds, right? 5, 10, 15. So we want to know the probability the student is 5 to 10 minutes late. That would be equivalent to figuring out that area. So area is equal to probability. Area is equal to probability. So if we can figure out this area, we would know the probability the student is 5 to 10 minutes late. All right, well, let's take that blue square and bring it down here. We know the height is 1 over 15. What's the length? 5 to 10. Well, 10 minus 5 is 5. So that's the length. So our area is going to be the probability, the area of that rectangle. All right, there's a common factor of 5. So we can say the area is a third, or like, that's the same as 0.33 forever. So that's what that probability is, because area is probability. And now let's consider this example. So this next example illustrates why we need intervals. So let's say we find the probability the student is 5.001 minutes late. And so really what that means, that's exactly 5.001 minutes late. So maybe that looks like 5.001 with zeros forever. So we want to know what's the probability of this one number occurring. Well, we know probability is area, right? So, but there's no, the base is just this one number. So here we have our little graph, and then maybe let's say or exactly one number would just be a line. So it would be a line with a height of 1/15. What's the width of a line? Isn't it like 0? Doesn't really make sense, does it? So this illustrates the point that continuous random variables have to be measured in intervals, because the probability of a single minute or a single number is 0. All right. So anyway, we need intervals for continuous variables. So now let's suppose class just began. There's a 20% chance that the student will arrive in blank minutes. So what's going on in this scenario is we're going backwards. All right, so we have this set up, our distribution, and it's a 20% chance, right? That sounds like a probability to me, and probability is area. So perhaps that 20% looks something like this. All right, since class just began, it starts at 0. And we want to know what that minute is, what X represents as a minute. So there's a 20% chance that the student will arrive in X many minutes. All right, well, we know 0.2 is the area. So base times the height is equal to the area of that rectangle. Okay, so we just have a linear equation to solve. We can multiply both sides by 15. 15 times 0.2 is 3. All right, so a nice little equation to solve. So there's a 20% chance the student will arrive in 3 minutes. Okay, so that just got us used to our continuous random variable. We need intervals. Area is probability. The continuous random variable we're going to work with often is the normal curve. So most distributions are not normal. Distributions that are symmetric and bell-shaped are said to have the shape of a normal curve. All right, so instead of saying bell-shaped from now on, we're going to say normal. If a continuous random variable is normally distributed or has a normal probability distribution, then the relative frequency histogram has the shape of a normal curve. All right, and then here's our example. So this would be considered a normal curve. So it looks like it's bell-shaped, symmetric. All right, and when we draw our curve, we have points of inflection. And inflection is where the curvature changes. So notice at the top of our normal curve, it's like a cup pointed downwards. Then after the inflection point, we flip our cup up, and now the cup is pointing upwards. So downward cup between the inflection points, after the inflection points, it's like we turn our cup over. All right, so we call this concave down, then afterwards it's called concave up. So sad face, half a smile face. Okay, so the inflection points are where the curve changes, and they happen at the same spot at 1 standard deviation away from the mean. So they happen at mu minus sigma and mu plus sigma. Okay. So let's compare two normal distributions. So this first one on the left, notice our means are different, so that would shift the curve horizontally. The standard deviations are the same, so it does have the same spread. These two curves have the same spread, but they're just shifted. And the two curves on the right have the opposite situation. The means are the same, but the standard deviations are different. All right, so remember, sigma of 1 means it's closer together. Standard deviation of 2 means the data is further apart. All right, so more spread out for sigma 2, tighter for sigma equals 1. Okay, so while this graph with sigma equals 1 is more narrow, remember the area under the curve still has to be 1. So to compensate for the narrow length, to make the area 1, we have to be taller. When the standard deviation is 2, we have a wider base, but because the area has to be 1, it's going to be shorter. Okay, so let's talk about the properties of our normal density curve. So first of all, it's symmetric about the mean, just like a bell-shaped curve. The highest point happens at the mean. We saw that the inflection points occur at mu plus sigma and mu minus sigma. And the area under the curve is 1. Okay, so some other things. Let's draw a normal distribution. There will be our mean, and we'll draw our inflection points. So remember, that's where the curvature changes. So sometimes I just like to draw some marks. So mu is the highest point. Let's say that's the inflection point. And we want to make sure everything's symmetrical. So across the way, there's our other inflection point. And now this is our upside down cup or bowl or sad face. And then after our inflection points, we're going to have a happy face. And then make sure the lines don't touch the horizontal axis. Okay, so that's the first thing I wanted to write. The normal curve goes on forever. And when that happens, so it goes on forever, it never touches the x-axis, horizontal axis. That concept is called a horizontal asymptote. An asymptote is a line that approaches a value forever, but never touches it. And we go off to positive infinity on the right. And then over here, this horizontal asymptote goes off to negative infinity. All right, the other thing is we know it's symmetric. We know that the total area under the curve is 1. So if we cut our curve in half like this, because of the symmetry, guess what the area under half the curve is? Yeah, we could say 1/2. Or, alternatively, we could say 0.5 as well. But that's just because it's symmetrical. And the area under the curve is 1. Okay, so we already talked about one interpretation of area. Let's scroll down to look at the other interpretations. So the interpretation of the area under a normal curve, we have two. One has to do with the population and one has to do with an individual. So the first one is that the probability, how we interpret the area under a curve, we can say it's the probability that an individual has the characteristics described by that interval. And the second interpretation has to do with the population. We would say the proportion of the population that area represents the proportion of the population with the characteristics described by that interval. Okay, so let's put that into practice. Let's look at a real example. Here we have that the weights of giraffe are approximately normally distributed with mean 2,200 pounds and standard deviation 200 pounds. So look at, they tell us approximately normal. All right, so let's draw a curve, part A, with the parameters labeled. This means the mean. I'm looking for the mean. And I'm looking for the inflection points. And do your best. I want it to be, approximately bell-shaped, symmetry. I'm also going to make sure you have those horizontal asymptotes. So let's see what I expect from you guys on an exam. So the mean is 2,200 pounds. And to cover our units, we could say weight in pounds. So we don't have to write the units over and over again of giraffes. Always nice to label your graphs. Okay, so then we have the 2,200 pounds. And the inflection points are 1 standard deviation away. So we have to go, standard deviation is 200 pounds. So let's add 200. So 2,400. And subtract 200. Okay. So again, I like to kind of make my marks. There's my highest point at the mean. My inflection point should be at the same height. I have one curvature between the inflection points, and then after the inflection points, I have a different curvature. And I'm looking for horizontal axis or horizontal asymptotes. Make sure those green arrows do not touch the horizontal line. All right, so let's see what part B. Shade the area under the normal curve to the left of x equals 2,100 pounds. All right, well that's about halfway between 2,000 and 2,200. Okay, so they want us to shade the area to the left. All right, so like less than 2,100 pounds. Now, suppose the area under the normal curve is 0.3085. So I'll just write that, 0.3085. Okay, give two interpretations. So remember, the first interpretation has to do with the individual. The second one has to do with the population. That's what we just did before this example. All right, so let's see what this is going to look like. So our first interpretation is the probability of an individual. So we would say the individual in this case is giraffes. So the probability of an individual, so a giraffe, so the probability that a giraffe, single giraffe, and then that interval represents less than 2,100 pounds because we're going to the left of 2,100 pounds. That probability is 0.3085. All right, and then the second interpretation is the proportion of the population. So our second interpretation is we could say that the proportion of all giraffes who weigh or that weigh weighing less than 2,100 pounds is 0.3085. And there you go.